Hey guys, and welcome to my video on 5-2a, Systems of Nonlinear Equations. To start us off, I have you looking at the following multiple choice question. Two equations were graphed on the set of axes below. Which point is the solution of the system of equations shown on the graph? Now, in the last part of this unit, we talked all about finding solutions to systems of equations, but they were all linear, meaning they were two lines. And the solution to our systems were the points of intersection. So here in this graph, we're not given two lines, but instead we're given a parabola, right, this guy, and a line. So now this idea is still the same. Our points of intersections will still be the solutions to our system. So we have two possible solutions now. We have the point 1, 2, 3, 4, 5, 6, 7, 8, comma 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But we also have this point over here, which looks like it's 1 3/4, negative 1 3/4, comma 2. So let's fix that. Okay, so now looking at the multiple choice, only one of those is our answer. Okay, but how these nonlinear equations differ from linear equations is that the number of solutions we may get is going to be different. Okay, so we're going to look at a bunch of examples today of systems of equations, some with lines, some with parabolas, some with others, and we're going to see the similarities and differences between how we solve systems of linear equations versus things that are nonlinear. So to start us off, I'm going to ask that we graph the following system. So remember, to graph a system of equations, we need to make sure both are on the same coordinate plane, right? And we want to make sure we include as much information as we need to show our grader what we're doing. So first I'm going to graph this one. Now when you stick it in your calculator, remember this would be y1, this would be y2, and we get our table, okay? This is what we should see. y1, y2. So we should see negative 4, 10, negative 5, negative 3, 4, 4, negative 2, 0, 3, negative 1, negative 2, 2, 0, negative 2, 1, 1, 0, 0, 2, 4, negative 1, and 3, comma 10, negative 2. Now, there's a reason why I chose these values. First off, we know that when we're graphing a parabola or a quadratic, we need to make sure we have our vertex within our graph. Then we pick a few points above it and a few points below it. Now, looking at y1, right, that's our parabola. Remember, we're looking for that matching pattern. So if we take a look at how this goes, it goes 10, 4, 0, negative 2, and then has the exact same pattern on the other side. Now, although this table doesn't show it, my vertex will be somewhere in between negative 1 and 0. Okay, so that will be where my vertex is, but it doesn't show up on this table. So I'm going to graph those points. Negative 4, negative 10, 1, 2, 3, 4. Wait, 1, 2, 3, 4, comma 10. Up there. Then we have negative 3, 1, 2, 3, 4. Negative 2, 0, negative 1, negative 2, 0, negative 2, and the same on the other side. Okay, so that's the graph of our quadratic. Now remember, we want to make sure we label each one. So y1 is equal to x squared plus x minus 2. Okay, now we're going to graph our line. Now, again, the thing with the line is that we want to make sure we cover the entire coordinate plane to make sure we include every possible point of intersection. So although I only put these in my table, right, I can do the trick with lines by starting at my y-intercept of +1 and going down 1 over 1. And so I'm going to graph that. Okay, so we connect those points and we label it y is equal to negative x plus 1. All right, so now we have our graph. At this point, we should be able to see where our points of intersection are. We have a point of intersection at 1, 0, and a point of intersection at 1, 2, negative 3, 1, 2, 3, 4. Now, great that we can see that on our graph itself, but if we had looked at our table, there's actually some clues that we have points of intersection, okay? And so in our table, our points of intersection are going to show up in places where my y2 value and y1 value are the same for the same x value. So this is where we see the point negative 3, 4, which showed up here. And we also see the point 1, 0 that showed up here on our graph. Okay, so when we're solving by graphing, it's the same process. We just may have more than one point of intersection. Okay, so now the question is, how do we do this algebraically? Okay, how are we going to follow that? Solve that same system of equation algebraically. Now with linear equations, remember we had two methods. We had substitution and we had elimination. We are going to stick with substitution for this type of system. Okay, we're going to try and make a substitution somewhere within our equation so that we can solve. Well, remember, when we have a point of intersection, the y values are going to be equal. Okay, which means that I can substitute this y value in for this y value into that equation. So what do I mean? Well, basically I'm saying set the two equations equal to each other. Minus x plus 1 is equal to x squared plus x minus 2. So now, how do we solve this? It's not going to be the same as the substitutions we've seen before, because now we have a quadratic, which means we need to use the methods for solving quadratics. So let's review that for a second. When we have quadratics, we have three main methods. We have factoring, we have complete the square, and we have the quadratic formula, all of which I'm actually going to show you throughout these videos. Okay, so for this one, I'm going to choose factoring. Okay, now if we remember how to solve by factoring, remember we need to get the equation equal to 0 so we can use the zero product property. So I'm going to add x on both sides. Plus 2x and subtract 1. X squared plus 2x minus 3. Okay, so now we have one quadratic set equal to 0. We look to see if we can factor it. Well, in this case, we're going to look for two numbers that multiply to negative 3 and add to a positive 2. Well, those two numbers are positive 3 and negative 1. So those go directly, positive 3 and negative 1. Okay, now because it's all set equal to 0, we can set each one of our factors equal to 0, and we get x is equal to negative 3, and x is equal to a positive 1. Now we can't stop there. Remember, a system of equations has an answer that is an ordered pair. Okay, so that means we need an x and a y value. So that means for each one of these x's, we now need to plug it in to one of these equations to find the y value. Now, technically, you can plug it into either one. However, one is significantly easier than the other. I tend to always plug it into the linear equation because it's less calculations. So, y equals negative x plus 1. First, we're going to plug in negative 3 for x. So, y is equal to negative 3 plus 1. So that's a 4. And y is equal to negative 1 plus 1, which is 0. So how does this work? Well, when I plugged in negative 3, I got 4. So together, those are one of our solutions, negative 3 comma 4. And when I plugged in negative 1, I got 0. Again, as a pair, those are one solution. So if we take a look back up at the graphing question that we just did, we see that we have the same answers. Okay, so we're going to stick with substitution for these. There are ways to do elimination, but substitution will always work. So for the rest of the questions, we're going